In this lesson, I'm going to give you an introduction on how to plot. This is very useful because you're going to need to know how to do this to present your information to other people. Let's create a couple random data sets and explore how to plot them. So the first data set I want to create, we'll just call it X. We're going to use the random normal function to create a random series of numbers that is 1,000 in length. Similarly, let's create one from the uniform distribution. The function for that is RUNIF. Throw in 1,000 so that they're the same length. Now, a new function I want to introduce is the cumulative sum function, which does a running sum of the data set. So to use this function, it's very simple, and we're going to create a new variable called csum of x. We'll use the cumulative sum function on that vector. So we're going to use that in just a minute. Plotting is very easy. We can submit a vector of information to plot as a single argument. The plot function is just plot. If I execute it with the first object that I created, it's going to produce this plot. And we can see that everything is set to a default. We have not added in any other arguments. So it's going to show us a point for each observation. And it puts in an order from 1 to 1,000, depending on where it is in the vector. Right away with this data set, you'll notice that the values bounce randomly around 0 and mostly stay within -2 and 2. And that's because of the distribution that we specified using the rnorm function. If we plot our uniform data set, it's going to look a little different. It's going to be more evenly spread out between 0 and 1. Now let's plot the cumulative series of our x vector. Now, this plot looks very similar to market data, and this is known as a random walk, which is a succession of random steps that are added up to each other. And every time we plot a similar series, so we're going to plot the cumulative series of a random normal vector, it's going to look a little different. Plotting points like this can be confusing to look at, so let's try plotting different types. So I'm going to create a new series, and what we're going to do is we're going to plot this series, and we're going to set a new argument called type to equal the type that we're interested in. If you want to plot a line, you need to set your type to equal the letter L in quotation marks. And you can see here when we zoom into the plot that now it's showing lines. From one point to the next point, it's going to connect it with a line instead of having a point at each observation. Now let's do the same plot with the cumulative sum and zoom in. So we can see that this looks very much like some financial data or just a random series. Could really be anything. So type L is going to produce lines for us. If you want to use points, which is the default, it gets set to P. Some other interesting ones are H, which is going to produce a histogram. And you can see that for the cumulative series, it looks rather funny because it's going to bring whatever the observation is all the way down to 0. And so you can kind of see how many of the observations are below and how many are above. Another interesting one is O, and this creates lines and points. And lastly, if you want to use steps, we use S as the type. And it's actually kind of hard to tell because our series is really big, so I'm going to create a smaller series. So let's just do rnorm of 10. And this is how steps look. So my first observation is down here at -5, and my second observation is up here at 1.5. But instead of jumping with the line between the points, it's going to carry that observation to the next index, and then it will jump up. Now, we can also adjust the colors. So black is the default, but we can specify which color we want to use. So let's go back to our cumulative series, and we'll specify type as line. We're going to set our color to be blue, and it's very simple to do. The argument is COL, and we're going to set it equal to a character string, which is the name of the color. And there we go. You can see that it's now blue. Now you can really throw in any well-known color, and there are actually hundreds of colors we can throw in. But we'll just use some basics for now, such as red, green, blue. Every time we use the plot function, R is creating a new plot object. And you can see that in the RStudio environment, we can actually go back through the plots that we've created using these arrows. Use the zoom function to zoom in, and get a bigger picture. And then you can export these plots as different file types, such as PDF. If you want to delete the plot, use this little button here. And if you want to remove all the plots, use the Clear All button. So that's for some very easy functionality in RStudio. Okay, so let's plot our original cumulative series of X. We'll set type to be line, and we'll set the color to be blue. The question now is, how can we add more information to this plot without creating a new plot that's just going to erase the one that's already here? Well, we can use the lines function to add more lines to the existing plot object. So let me try adding some lines, which is going to be the cumulative series of another random normal data set. We'll set the color to be red. We can see that something funny happened here. We threw in a random data set that exists mostly below 0, so it gets cut off by the plot that's already there, and we can just see little peaks of it here and there. So how can we fix that? When we originally create the plot object, it's important to set your Y and X limits, because this is going to determine how the plot looks the whole time you're using it. So let's create a couple more random data sets. We'll do Y and Z. And I'm going to cbind all of the data together as a random data set. Using the cbind function, I'm going to throw in my cumulative series of X, Y, and Z. So now when we initiate our plot, we're going to plot the cumulative sum of X first. We can set a new argument, which is called ylim. And ylim is a small vector that takes two different numbers, and it's going to take the minimum and the maximum that you're interested in. For the minimum, I'm going to use the minimum function on the random data set. And for maximum, I'm going to do the same thing, except use the maximum function. So now you can see what happened. It's now created a bunch of extra space below our X vector, and this is going to be eventually filled in with the Y and Z information. So now we can use our lines function again, and we'll do the csum of Y, and we'll set the color to be green. And then we'll plot Z, and we'll set the color to be red. So now all the information is displayed in the plot and nothing's being cut off. And you can see that it was the Y vector that sort of dipped all the way down to past -40. Now you can also add points to a plot after you've created the plot object by using the points function. And this time, why don't we throw in the average of the 3 series at every index? So to do this, we can use the row means function on our random data set, which combines all of the data in columns, and then we'll set the color to equal orange. So you can see that it kind of stays around 0, but at each point, it's going to give you the average of each vector at that index. In this lesson, we started talking about plots and specifically how to generate them and add lines and use some of the different arguments. In this lesson, we're going to talk about some other plotting arguments. Ahead of time, I just created a few lines that are running the cumulative sum on some random series. So we're going to have X, Y, and Z. And then I'm going to combine them all together to be one full random data set. Instead of setting the Y limits to be max and min, let's just try using the range function instead. So I'm going to plot first the csum of X, which is going to stand for cumulative sum. We're going to specify type to be line. Color, we'll set to blue. And for our Y limits, why don't we just make it the range of our random data set? And we'll see if this works. It looks like it works, but we won't be able to tell until we throw in the other lines. But you can tell because there's sort of a bigger gap up here that most likely it captured the minimum and the maximum of the data set. Now we're going to go ahead and add in the other data types, the Y and Z vectors. So first let's throw in Y, and we'll set the color to be green. And now I'm going to show you a new plotting argument called LTY, and this is line type. So there are many different line types we can add. That includes dashed lines, dotted lines, etc. By default, it's set to 1. If you set it to 2, it's going to look a little different. And we'll see what that looks like in just a second. And now I'm going to plot the Z line. We'll set color to be red. And for the line type, let's make it 3. when we zoom in, you can sort of see what's going on. So the green line now has dashes, while the red line has little dots. And this can be very helpful, especially when you want to separate different data types, because sometimes when they become clustered together, it's hard to tell what's going on. Now, another plotting argument that can be very helpful is line width. As you can tell when we looked in here, these are very fine lines, and it can be kind of hard to see them. Why don't we just make them thicker? So for line width, use the LWD argument. By default, it's set to 1, and as you increase the number, it's going to increase the thickness of that line. If you throw in a decimal, it's going to make it smaller. So why don't we make the line width 3? And you can see right away that now it's much easier to read. And if we throw in our other lines, there we go. It's a little easier to see now. To add a title to the graph, we can use the title function once the plot object has already been initiated. And you want to use main as the main title of the graph, and we'll call it stock prices, even though they are completely random. And we can set the color of the font using call.main. We'll set it to be black. And we can set font.main. We'll set it to be 3. Now, setting the font.main to equal 3 means that it's going to italicize the title. Now, we could do this again and set it to 1, and you see how it normally looks like, but you can see that causes a problem. It actually tries to create the title twice. You can't really tell till towards the end when they get shifted a little bit. Now, we can also throw in a title into the plot function instead of using the title function after we create the plot. In this case, you want to just set the argument main to equal whatever title you want to give the plot. Now, we can also change the x-axis and y-axis labels. You can see right now that they're just set to be the name of the x object that I threw in and the index. But instead of doing that, why don't we set xlab, which is the label for the x-axis, to equal time. And then we'll set the ylab, or the label for the y-axis, to equal price. And then we can throw in our other lines. And there we go. Now this is much more informative. In this lesson, I gave you some more information about how to set different plotting arguments. And that includes the labels for the x and y axis, how to use the range to set your limits, and how to give a title to your plot. In this lesson, I will be talking about some specific plot types, bar charts and histograms. Many of the arguments we have talked about so far can be applied directly to the bar plot and histogram functions. So let's load some new data. First, let's make sure we have our mass package loaded. And then we're going to use the data function to open up a tab of all available data sets. So I'm going to scroll down to the mass package. You can see it here, data sets and package mass. I'm going to look for the Caith data set. And we can see it right here. So this data set describes hair and eye color of over 5,000 individuals in the county of Caithness, which is a northern portion of Scotland. So to load the data set into our environment, we'll just use the data set name as an argument in the data function. And we can see that it's now appeared in our environment. So it's a rather small data set. It's a 4x5 matrix describing how many individuals fall into each combination of eye color by rows and hair color by columns. So let's collect total values of eye colors and hair colors. We're going to use the row sums function on the data set to collect all the eye colors. And then for hair color, we'll look at the column sums of the data set. So for bar plot, it's very easy. We're going to use the bar plot function and enter in the data that we're interested in looking at as an argument. And here's your first bar plot. If we look at hair color, there will be 5 different columns because we have 5 different hair colors. You can see that there are very few people with red hair or black hair. Let's add some more arguments to make this look a little nicer. So we'll look at eye colors. We'll set our title to be eye color, and we'll label our x and y axis. And lastly, we'll use a new argument called density, which I'll explain in just a second. We had an error because I mistyped the density argument. After I correct that typo, it should work. So now we have our x-axis and y-axis labeled, along with the title for the chart. The density function fills in each bar with a series of diagonal lines, and the higher the number, the more dense it is. You can see that for the dark, fourth parameter I specified for density is 20, while for blue it's 5, so there are less lines. Now let's try a bar plot on the whole dataset and see what happens. It actually returns an error because the object that we are entering in as the argument of interest must be a vector or a matrix. We can easily solve this by wrapping an as.matrix function around the dataset. So it's going to be plotting a bar plot of kth as a matrix and not as a data frame. So you can use the class function to see what type it is. So before it was a data frame, and then when we enter it into the bar plot function as a matrix, it works just fine. So you can see that for each bar, these are different hair colors, and then it's breaking down each bar into eye colors as well. Now we can add colors to this to make it look a little nicer. Because each bar is broken down into 4 different categories of eye color, I specified 4 different colors as a vector for my color argument. Now we can plot the reverse of this with the columns sorted by eye color by using the transpose function introduced in an earlier lesson. We're going to wrap our dataset in one more function, and we're going to transpose the matrix form of the kth dataset. And now we have only 4 bars, one for each eye color, and then each one is broken up 5 times into hair colors. Another way to lay out this information is to set an argument called beside to be true. So I'm going to set my beside argument to be true, and it's going to look different. Instead of being stacked up on top of each other, it's putting the bars right next to each other. So for each hair color, it's breaking out the information by eye color. So from this, it's easy to infer that people with lighter colored eyes tend to have lighter colored hair. Now, histograms are just as easy. Histograms describe the frequency of observations. In this case, it will be calculating how many times certain groups of numbers appear. So if I use the histogram function, which is HIST on our dataset, we get an error because it says X must be numeric. Its class is a data frame, so if we change it to as.matrix, maybe we'll get some better results. So this plot is simply telling us how often we see a certain frequency. Here we have one value between 800 and 1000, while we have 11 values between 0 and 200. Now we can also determine how many breaks there are. So what I did was I refined the bar. So before, it used 5 different breaks, from 0 to 200, 200 to 400, and so on. In this case, it's going from 0 to 100, 100 to 200, and so on. Now let's look at a histogram of random normal numbers. I'm going to create a data set called R, which is going to be 1,000 random normal numbers. If we look at a histogram of R, we should start to see what is called a normal curve, or a bell curve. If we increase the number of observations, let's say we have a random data set of 10,000, I can plot the histogram of R, and I'm going to set breaks to equal 100. We can see that it's getting closer to a true bell curve. What if we tried a chi-squared distribution? Although I won't talk about it in depth, chi-squared distribution is used in many statistical tests, including whether a sample frequency distribution is consistent with a theoretical one. DF stands for degrees of freedom, and as we change degrees of freedom, you can see how the chi-squared distribution begins to move away from the y-axis. So I'm going to use the RCHISQ function, which is going to pull random numbers from a chi-squared distribution, initially set my degrees of freedom to be 2. So we can see with degrees of freedom of 2, the distribution starts pretty heavy around 0 and quickly drops off. And then when I set degrees of freedom to be 3, you can see that's sort of starting to push away from that y-axis. So in this lesson, I gave you an introduction to bar plots and histograms, which are both pretty easy to execute, and they're a good way to begin exploring data. In this lesson, I will be explaining how to set up scatter plots with correlation information. Let's load the CARS93 dataset. So if we look at all available data to us using the data function, there's a dataset called CARS93 in the mass package. which is very useful for learning R. If your mass package is not loaded already, use the require function on your mass package, and it will load the package for you. So here's the data set, and it's data from 93 different cars in 1993. So to load the data set, I'm going to throw in the name of that data set, cars93, as an argument into the data function. Let's see what it looks like by using the head function, and we'll get the first 5 rows. So we can see that there's a lot of information here, and we can actually use the nCall function to count the number of columns. 27 different variables is what we're looking at. There are a lot of quantitative variables and also qualitative variables. So let's take out a few variables of interest, specifically price, miles per gallon in the city, engine size, and weight. Before we do this, we're going to attach the cars93 dataset. This function allows us to pull data without specifying which dataset every time. To create a scatter plot, we use the plot function, but we need to specify an x and y coordinate. Because I've attached the cars93 dataset, I don't need to specify, for example, cars93 $price. This is how we would normally call the column name of interest when we haven't attached the dataset. So when I plot these two variables against each other, price versus weight, the scatter plot is produced. We can see that there's sort of an uptrend. So as the price increases, the weight is also increasing. Better way to think about this might be a car that is heavier, might be bigger, might be more expensive to produce. As a result, will cost more. Let's look at miles per gallon in the city. In this one, we can see a downtrend. And as the miles per gallon in the city decrease, we tend to see a higher price. That might not be true in today's world, but back in 1993, I guess it's true. Now, why don't we look at weight versus miles per gallon in the city? This trend also makes sense. As the weight of the car increases, it gets worse gas mileage. Now, we can quickly add a regression line to the scatter plot using the abline function. It works very similar to the lines function, just a little differently. There are different arguments we throw in. For abline, we can throw in a linear model. As we'll see pretty soon, LM is a function that runs a linear regression. I will just brush past it for now so you understand how this works. When I execute this code, it plots the regression line on top of the scatter plot. Now this function allows us to add any specified line. So instead of the linear function, why don't we just look at the max of one of the variables, miles per gallon in the city. This isn't entirely necessary because you can tell that this point right here is the maximum, but sometimes it can be helpful. So H will add a horizontal line, while V, as an argument, will set a vertical line. In this case, why don't we look at the max of the weight, and it will show us where it cuts off. So I've added 3 different lines, the linear regression line, a vertical line, which is the maximum weight, and a horizontal line, which is the maximum miles per gallon in the city. Now let's look at the pairs function, which allows us to build multiple scatter plots at once. It uses some funky notation, with a tilde followed by summing the columns of interest. So you can see that the pairs function took each of the 4 columns I'm interested in and built a scatter plot of it versus the other 3 columns. So this is a nice way to quickly look at information in your data set when you first start working with it. Dot chart is another helpful graph. It lays out information on a horizontal line that can easily be compared with other observations. So let's look at a dot chart of the miles per gallon in the city. This doesn't really tell us very much right away because there's no information about what each point is. So we actually need to specify what our labels are. So as an argument, I'm going to set my labels equal to the manufacturer column and the model column pasted together. So this is a little messy because the labels are too big, and there are too many of them. Before we fix the label sizes, why don't we order the miles per gallon in the city so we can right away see which one is first compared to which ones are worse. Create a new data set called order cars. It's going to be the cars93 data set. I'm going to use square bracket notation to subset, and I'm going to have it return to me in order by miles per gallon by using the order function. So this order function tells us the order of miles per gallon in the city from high to low by its row values. We then reorder the Cars 93 dataset. When we throw in this vector of numbers, it shuffles around the rows. We'll be seeing a lot more of this function later on, so don't worry about becoming too familiar with it yet. So now I'm going to attach my new Cars dataset, which is called order Cars. When I do this, this message pops up because it's telling me that the original attached dataset, Cars 93, which share all of the same variables, are now going to be hidden. So the Cars 93 dataset is no longer attached. So now let's try our dot chart again. And we're going to specify another argument called CEX, which is going to tell us how big to make the labels. By default, it's set to 1, so why don't we try setting it to 0.5? There we go. Looks better. And it's now in order of the Geo Metro, which has the best miles per gallon, all the way down to the Chevrolet Astro, which gets a measly 15 miles per gallon. In this lesson, I gave you an introduction to scatter plots, how to do multiple scatter plots at once, and also dot charts. In this lesson, we're going to talk about probability plots. And these are very useful for exploring data and also for thinking about statistical concepts. First, let me introduce the QQ plot. When we begin to explore data, we may want to explore how closely one vector of data matches the distribution of another. So let's start with the easy QQ norm function, which compares any data vector to a normal distribution. So I'm going to create a random normal vector of 100 observations. And then I'm going to use the QQ norm function on that data set. After we execute the QQ norm plot, we can add a QQ line which adds a line to a normal quantile-quantile plot, which passes through the first and third quartiles. The closer the data points match the line, the more closely the data vector follows a normal distribution. So let's add that line real quick. QQ line X. And when we zoom into this plot, we can see that it matches pretty closely. Of course, there are some fluctuations, but I'm pulling random numbers from a normal distribution, so we expect it to be somewhat close. Now let's load the Cars 93 dataset using our data function. I'm going to attach the dataset. Now when I attach the Cars 93 dataset, it's sharing a lot of variables with some data I had loaded in here from previous lessons. The following objects are now masked from these two different datasets, but you can ignore that. All it means is that it's going to no longer pull information from those two datasets when I call the variable names. So now let's try the QQ norm function on one of the Cars 93 variables. And then I'm going to throw in the QQ line, and we'll see how closely it matches a normal distribution. And we can see that it doesn't do too great. On the tails, it doesn't meet the line at all. A similar function is QQ plot. And for this function, we enter two different arguments to compare the distributions against each other. No longer concerned about normality, but how closely the two datasets match each other. By doing this, we can compare any two datasets to see if they share some underlying characteristics. Secondly, we can compare a data vector to different random datasets to see how closely they match that distribution. So I'm going to create a random dataset called Y. It's going to be 100 observations. We can use the QQ plot function to compare X and Y, which both come from a normal distribution. So we should expect them to line up and have similar distributions. For QQ line, use the second argument that you threw into QQ plot. So we're going to use Y. And we can see that there's a little more noise, and that's because one distribution matches somewhat closely to the normal distribution while the same for the other ones. So they can be even further apart. Now let's compare our random vector X with miles per gallon in the city. And we can see that it looks very similar for when we used QQ norm on the miles per gallon. And we expect that because the X vector comes from the normal distribution. So now let's compare two of the variables from the Cars 93 dataset. We'll compare miles per gallon to engine size. So they look like they're probably similar distributions because of how they line up so well. Let's add in QQ line. So why is the QQ line all the way out here all of a sudden? Well, the data are actually on different scales or magnitudes. So we first need to scale the data using the scale function. The scale function centers the data around 0 and shrinks it so that the magnitudes of the datasets match each other. So let's run the QQ plot again, and for each argument, we'll wrap the variable of interest inside the scale function. And then for our QQ line, we'll do the same thing. We're going to scale our miles per gallon. Now the line is where it should be. We can see that these distributions match each other pretty well, except for at this extreme tail over here. So let's look at the scale function a little more closely. Create a vector of numbers, and I'm going to scale that vector. It's going to return each element scaled, and it's going to show you how it centered it and how it shrunk it. So if we calculate the mean of that same vector, we can see that the scaled center is the same. And if we use a standard deviation on x, we'll see that that's where it gets the scale from. If I subtract the mean from x and divide it by the standard deviation, we should get the same results as the scale function. And you can see that that's the case, although it returns them slightly differently. We can see that the first element is negative 1.4, same as with the scale function. Now, what if we wanted to compare the distribution of miles per gallon to a different distribution than the normal data set? Why don't we try the chi-squared distribution? So I'm going to set up a QQ plot, and I'm going to use the scale function, and I'm going to get some random numbers from the chi-squared distribution. And I want to make sure that I have as many observations as there are in the Cars 93 dataset. So I'm going to throw in the number of rows of Cars 93, and that's how many observations of my random chi-squared dataset I'll have. Next, I'm going to compare this to the scaled version of my miles per gallon. And lastly, for this R chi-squared distribution, I can't forget to set my degrees of freedom. So I'm going to set my degrees of freedom to be 5. We'll see how that looks to start off with. Lastly, I'm going to throw in my QQ line for the scaled version of the miles per gallon. We can see that the distribution of miles per gallon fits much more closely with the chi-squared distribution than it does with the normal distribution. There's still some error off on this tail, but it still looks better at the lower tail than it did before. In this data set, we talked a little more closely about how to explore probability plots and how to explore what distributions different variables might have. And this can be very important for when you're picking which models to run on your data. In this lesson, we're going to talk about combining and saving graphs. We can combine plots using two main functions, par and layout. So first, let's load the Cars 93 dataset from the mass package using the data function. We're going to attach the dataset. And again, you're probably familiar with this by now, but you can ignore these little warnings. They're basically just saying that before I loaded the most recent Cars 93, that there are other data objects that contain those same variables. So let's plot a couple scatter plots. We're going to set X to be weight and Y to be miles per gallon in the city. And then we can also plot as a scatter plot weight versus price. So now we have two plots, but they're on different plot objects. We can combine them easily using the par function. So when I execute this par function, nothing happens. And why is this? Well, we simply set the graphical parameters. Now, when we create plots, it will follow those parameters. Now, this parameter set will create a layout of two plots with this argument mfrow equaling the vector of 2 and 1, meaning 2 rows and 1 column. So let's re-execute our plots. I return an error saying figure margins are too large. And that basically just means that my little plot window here is too small. So if I expand this up, it should work just fine. And now let's plot our second scatter plot. Now we can do any number of plots as long as they fit into the plot window. These margins are another graphical parameter, and you can see that they're kind of large here. Now let's try setting our graphical parameters to be 2 by 2. So we're going to try and plot 4 different scatter plots. And this is how we put plots side by side. Now let's talk a little bit more about the margins. So the gap between the edges of the different plots are called the margin. Look at what happens when we shrink our plots in the RStudio window. So if I lower this, we're going to see that the different plots shrink while the margin stays the same size. Eventually, if we shrink this window to be too small, the plot disappears and it says figure margins are too large. We can make up for this margin error by changing our margins using an argument in the par function. We won't worry about that for right now because it's not a big issue. But if you go to this website, there's some very good information about how to easily change your margins. And you can see it right here. It's on the RBloggers website. Now let's talk about the layout function. The layout function allows us to do more complicated plotting layouts. It works by taking a matrix of integers as a mathematical layout. So first let me create a matrix for you to help explain this a little better. We got an error because I misspecified the true argument. So instead of being lowercase RUE, it needs to all be capital. I'll just do capital T to make it easier. So this matrix of numbers, you can see goes 1, 2, 1, 3. When I throw this into the layout function, it's going to put one plot over the ones, a second plot over the 2, and a third plot over the 3. So I'm going to put this matrix inside of the layout function, and then we can run some of our scatter plots again, and we'll see how this looks. So this is a nicer way to do it, especially if you need 3 plots or you want to emphasize one over the other 2. Now we can save plots in many different formats, including JPEG, PNG, and PDF, among others. RStudio makes it very easy. It keeps track of the different plots we have created, and we can easily save any of them using the export button in the plot window. So let's say I want to go back to a few plots ago, maybe this first one. I can save the plot as a PDF. Or the more recent one, let's say I export it as an image. Now it's saving these plots inside of your working directory. So if I sort my files by when they were modified, we'll see that I just created 2 plots, one as a PDF and one as a PNG. So in this lesson, I gave you an introduction to how to combine plots and how to save plots, and we'll be using these throughout the course. In the next section of lessons, I will be describing a few more data types and how to load and manage data. The first step is to talk about a special type of matrix called an array. It is similar to a matrix or vector, except that it has an additional dimension attribute known as DIM, and optional dim names. So let's explore this a little further. I'm going to create a vector of integers, numbers 1 through 9, and then I'm going to use the array function to turn it into an array. To explore the attributes of the 2 objects, we can use the attributes function, which we will be using frequently. This function simply lists the different attributes that have been assigned to the object. So x has no attributes, it's just a very simple numerical vector. But when we look at the attributes of our array, it has an attribute called DIM. Now this dimensional attribute only has one value, the number 9, meaning it is a one-dimensional object with a length of 9. We can use the dollar operator to extract the different attributes. So this can come in handy when we're iterating through loops. Let's create the array again, but set more dimensions. To do this, we're going to be using the DIM argument, and we're going to be setting it to be a 3 by 3 matrix. So this function right now is pretty similar to creating a matrix. Instead of using nRow and nCol for number of rows and number of columns, we're throwing integers in place of that. Now, the output of AX looks like a 3 by 3 matrix. And if we use the attributes function, we'll notice that the dimensional attribute now has 2 different numbers, one for number of rows and one for number of columns. And if we want to pull out only the number of rows or only the number of columns, we can use the square bracket subsetting at the end. If I put 1, it's going to give me the number of rows. And 2 is going to give me the number of columns. We can create arrays of higher dimensions as well. Now I'm going to change x to be a vector of integers from 1 through 12. And using the dimension argument, I'm going to be giving it 3 different dimensions. We have now created a three-dimensional array. We can subset the three-dimensional array by using the same square bracket subsetting, but this time we're going to use 2 commas and specify 3 different locations. So this, for instance, is going to return the observation that's in the first row, second column of the first matrix, which is 4. I can change this 1 to be a 2, and it's going to return 10, because it's going for the first row, second column of the second matrix. Now we can do standard operations to these arrays just like we can with matrices or vectors. Multiplying it by 2 will multiply each element in the array by the number 2. We can also use the square bracket subsetting to easily replace things. So let's look at what's in the first and second rows and the second columns of both matrices. If we look at AX again, we can see that this first column, 4, 5, is coming from the first matrix, second column, first and second rows. To replace things, we very simply have to assign them new values. And now when I look at my AX array, we'll notice that those have all changed to 0. So let's create an array again. I'm going to set the dimensions to be what they just were, 3, 2, and 2. Now we can change the dimensions of these arrays at any time by using the dim function. So this is going to replace the dimensional attribute of this object with whatever I'm giving it. So I'm going to change it to be C, 12, and 1. So it's going to be 12 rows and 1 column with no other third dimension. In this lesson, I gave you an introduction to arrays and how to manipulate them. In this lesson, we're going to talk about a list. A list is an ordered vector that can contain different classes of objects known as components. So I'm going to create some vectors of different classes. These different vectors that I created are all different classes, and they're also different lengths and have different dimensions. We can easily combine them all as one object using the list function. Now, when we look at X, we'll see the 3 different vectors that we just added. Now, if you subset the X object, which is a list, with the number 1, it's going to return the first object of that list, and here it returns the numeric vector. If I enter 2, it's going to return the letters, and 3 is going to return the vector of booleans. Now, what if you want to subset within a subset? To do this, we need to use double square brackets. When I execute this line of code, it's going to give me the first object of the list, and then it's going to give me the first element of that object. If I throw in a 2 in place of 1 in the double square bracket, it's going to return the letter A. Because the second object is a matrix, in the second part of the square bracket subsetting, I can specify which row and which column I'm interested in. And we can also use this notation to reassign different portions of our list. So instead of C, let's change it to be 4 Cs. And then when I look at the second component of that list, you can see that it's now been changed. Now we can also give each component of the list a name. So when we looked at X before, these were the names that were assigned to it. You can think of these as the indices of the list objects. Now, if we rerun our list command, we can change how this looks. The syntax is saying I'm going to create a list object which is called num, and it's going to equal my number vector. Similarly with strings and with booleans. And now when we look at the X list, you'll notice that the names at the top have changed. This allows us to subset using the $operator. Let's look at the attributes of our list. Because I specified names, our list now has these attributes known as names. And I can also pull them out using the names function. So the names of my X list are num, strings, and booleans. We can attach our list, and we no longer will need to use the special bracketing or $operator. So now, when I type num, it's going to return the number vector. Or if I type strings, it's going to return my matrix of letters. And finally, I want to detach my list. Well, I received an error because I had 2 T's, and detach only has 1 T. So now that data list is no longer attached and at the front of the system. Now we can collapse the list by using the unlist function. By unlisting the list, it creates a vector of all the objects and their elements, and in this case, forcing everything to be a string, as the string components of list X cannot be coerced into numbers or booleans. And lastly, we can add a new list component by using the C function. The first object I'll put as X, and then I'm going to create a new list component called date. And we'll just set it to be the character representation of our system date. And there you go. You can see the new component. So in this lesson, I gave you an introduction to lists, how to create lists, how to name the different components of lists, and also how to add new components to that list. In this lesson, we're going to talk about data frames. Now, a data frame is a special class of a list. It is a list of vectors that have the same length or two-dimensional array-like structure. Creating one is easy. Let's think about some simple city data. Ahead of time, I put together some quick information about 3 different cities: Seattle, Chicago, Fairbanks. So we're going to include the city name, the population of each city, the average high temperature, and a Boolean whether it's saying it's in the continental US or not. So we're working with 3 different classes of data here: numerics, characters, and Booleans. So I'm going to run this code. And then we're going to use the data frame function to turn them all into a data frame. Now each column is a component of this special list. If we look at the attributes of this city dataset, it's going to return the names, the row names, and also the class. Now we can subset this data frame using the very familiar ways, such as the square bracket notation, or we can also use the $sign. You may notice that the output looks a little different. It tells us the different levels of the column slice cities. This is because the strings were converted into a factor class, and we'll talk about what a factor class is shortly. There's an argument in data frame that is strings as factors. The default for this is true, and it turns any string components of a data frame into factors. If we want to see them as strings instead, we simply have to add that argument at the end of our data frame function. And you'll notice the strings as factors argument has a capital A and capital F. So now when I pull out my cities, instead of showing me what levels there are, it's just going to show me the data as character strings. Now there are 2 helpful functions to get a first look at any data frame. The first is str, which compactly displays the internal structure of the argument. So I'm going to use city data as the argument. It's going to show me the different variables that are involved and whether they're numerical, logical, or characters. It will also tell you how many observations there are. And then, of course, there's the summary function, which we have seen before. Now, the Cars93 dataset, which we have looked at before, is loaded as a data frame. So why don't we load that real quick using our data function? Well, before we do that, let's require the mass package to make sure we've loaded it. Now, when I use the class function on the Cars93 dataset, it's going to return data frame. And we can use str to get a compact look at the different variables. You can see that there's quite a bit of stuff here. And at the top, we'll see there are 93 observations with 27 different variables. Now we can see just by scrolling through that there are many factors in this dataset. If we would have set strings as factors to be false, then these all would be character vectors. Now a factor set is kind of nice because a summary function of a factor set will produce a frequency table. The cylinders variable is a factor variable. So let's see what happens when we look at a summary of that variable. So these are the different types of cylinder engines, including one rotary engine, and is showing the frequency of each category. So let's talk about some data conversions. We have discussed many data types so far: numerics, strings, booleans, vectors, matrices, lists, data frames, and a couple more. They all have slight differences, but there are functions that can convert between a lot of these data types. For example, you are already familiar with as.numeric, as.character, and as.logical from an earlier lesson. Now let me quickly create a vector, a matrix, and a data frame, and we'll explore how to convert between them. So we now have a short vector, matrix, and data frame. So to convert between these different data sets, we're going to use some as.dot functions. Now we can change our matrix into a data frame using as.data.frame. It assigns column names as v1 through v4. If we change our vector into a data frame, it's just going to give it the name of that vector. Now we can also force things into a list using as.list. If we try it on the matrix, it's actually going to take each element of that matrix and turn it into its own component of the list. So this list has 16 components. And of course, if we unlist that list, it's going to turn everything into a long vector. Now, these are just a few other ways we can use the as.dot functionality. If you're ever having a problem with a function failing as it can't use the current data type, simply try one of these functions and see if you can get it into the right class. It may not be apparent now how some of these functions can be helpful, but as you start using R more often, you'll see how useful they can be. In this lesson, I gave you an introduction to data frames and factor sets, what the differences are between these and a list, and also different ways to convert between data types. In this lesson, we're going to talk about how to load a couple different data types into your R environment. Let's first talk about the read.csv function, which is part of the base R package. So CSV stands for comma-separated values, and this is a very popular method for storing information. One reason it's so popular is that it's easy to work with CSV files in programs such as Excel. So with this video, you should find a small CSV file called simple.csv. Make sure you put it into your current working directory, and then we'll be able to use the read.csv function on that file. The read.csv function works very simply. You just need to enter in the character string version of the file you want to load, including the file extension. So we'll assign a variable the CSV file that we want to load. Now when we look at the attributes of this file we just loaded, it recognizes that there are a couple different variables, that it's a data frame, and that there are 6 observations, which are the row names. Now the reason it recognized that the columns had names is because there's an argument called header, which by default is true. When it's set to true, it automatically looks for column names. So if your data had no column names, we would want to set header to equal false. Let's see what that looks like. Right after stating the file I want to load, I'm going to set the header argument to equal false. And this time, it's going to look a little different. This time, it thinks that the column names of trial, mass, and velocity is one of the observations. It then gives the columns some default names, v1, v2, and v3. And you can think of those as just variable 1, variable 2, and so on. So this isn't what we want. It's always important that when you load in some data that you inspect it for the first time to make sure something like this doesn't happen. Now let's take a closer look at one of the individual variables. And we're going to use the class function on our test CSV, and we're going to look at the trial variable. Instead of having an underscore, I accidentally put a parentheses. So we received an error that it couldn't find the function test. And that time we received an error because I had an unexpected parentheses. I had one too many. When I look at the class of the trial variable from our test CSV dataset, it tells me that it's a factor. Now we can set another argument in read.csv called strings as arguments to be false if we want to ignore these factor classes. So the strings as factors argument has a capital A and a capital F. If we set it to false, we received an error because I misspelled strings as factors. I accidentally have an A in the strings part. So now when I look at this new CSV that we just reloaded with strings as factors equaling false, we can see that it doesn't look very different. But if I use the class function on the trial variable, it's going to tell me now that it's a character. Now another way to import data is through text files. Read.table is a function similar to read.csv, except that it looks for text files where each data point is separated by a space. So ahead of time, I quickly built this little text file. And it has 3 different variables, gender, height, and weight, all separated by commas, and then 4 different observations. So 4 different people with their height and weight. Now I can easily load this in by using the read.table function. I need to first state the name of the file I want to load, And then I'm also going to use the header argument and set it equal to true. Now this warning message, incomplete final line found, that simply means that where this cursor is blinking now is at the end of the data file and that there's no final empty line. So if I hit enter, now we have an empty final line and we won't see that error message. Now another thing to notice is that it didn't separate gender, height, and weight. It kind of pasted them all together as one variable. So there's another argument we can use in read.table, which is called a separation argument. For the separation argument, we have to enter in some character string that separates the data. So in this case, we know that the data is being separated by commas. So if I use a comma as a character string for the separation argument, then it will split up the data into its proper variables. Now, one nice thing about the RStudio is that I can edit CSV and text files directly in RStudio. So if I click on my person info text file, it's going to open up a tab showing you exactly what it looks like. Now, one nice thing about this is that if I hit Control F, I can make anything be the separation. For example, let's say I want to find all of the commas and replace them all with a space. I can hit this All button and it's going to replace every comma with a space. And it's going to tell you how many times that occurred. So now I'm going to save this. And then if I take out my separation argument from the text file, it will load it just fine because by default, the separation argument is going to look for a space and data in a text file format. In this lesson, we talked about how to load two very important data types, and that includes the comma-separated values, CSV, and the text file. The read.csv and read.table functions allow us to do this, and they're both pretty similar. They share a lot of the same arguments.